Okay, so welcome to lecture 12.1 of the group theory course. This is the first lecture of chapter 12, and today we are going to start discussing band structures, electronic band structures using group theory. And we start by a simple example. Chapter 12 considers a simple example of electronic energy levels in a cubic crystal. And the starting point, and also throughout this chapter, we're going to be mostly dealing with what it's called the nearly free electron model. And I think it's a good idea to take a few minutes and go back and describe the basics of the nearly free electron model, and starting, of course, with the even simpler approximation, which is the free electron model. So this is basic quantum mechanics. So if you have a free electron Hamiltonian, it has only the kinetic energy term, and we know that the eigenfunctions are plane waves, and the energy eigenvalues are of this form: h bar square k square over 2m. So this is a basic results from the free electron case, but it already, as we have seen before, introduces the wave vector k as a good quantum number for the electron, right? So, and the kinetic energy, which is in this case also the total energy of the electron, is proportional to k squared. Now, the nearly free electron model starts from the free electron case, but it takes into consideration the crystal potential. But one assumes that the crystal potential is sufficiently weak so that we can consider that as a perturbation. So this is the approximation involved in the nearly free electron model. So we can start discussing this model recalling Bloch's theorem that tells us what is the general form of the electronic wave function in the single particle approximation. And as we have discussed before, it has two parts. One is a plane wave part, and the other is a periodic function part. Okay? So the periodic function, as we have already discussed, we can expand into a linear combination of plane waves, and these plane waves, they are not a general k vector, but they are specific g vectors, reciprocal lattice vectors. So this is a discrete sum over all discrete set of g vectors, the vectors of the reciprocal lattice. And these coefficients c of k minus g, they are the unknowns of our problem. So the problem is, given a crystal potential, how one can determine the wave function. So in this case, since we use this plane wave expansion, so the problem reduces into finding out what are these coefficients. Okay, this is what's called the plane wave expansion of the wave function, in this case the Bloch's function. Of course, since the crystal potential is also periodic, we can also construct a Fourier expansion of the crystal potential in this manner, right? So the crystal potential U of R is, again, can be Fourier expanded in this manner, in which G's are G prime in this case are reciprocal lattice vectors, and so and then the what one does then is to put this into the Schrodinger equation for the time-independent Schrodinger equation for a single electron under a periodic potential is going to be the kinetic energy term plus this potential energy term and the idea is that you just substitute these particular forms of the crystal potential and the wave function, and in the end, after a few algebra steps, that leads us into a set of equations for the coefficients C, right? These are our unknowns. And this set of equations are represented in what we call the central equation. So the central equation is actually a set of many equations, one equation for each coefficient C, K minus G, right? And you can see that the crystal potential, U, in this case the Fourier transform U of associated to a wave vector G prime minus G, couples the coefficient at G and the coefficient at G prime, right? So, and this is basically what we call the central equation. So there are some algebra steps leading into this, but it's not our purpose to review them here. And this is it's something that we usually see in undergraduate condensed matter physics or solid state physics courses. Okay. So this is the central equation, and what we mean by a nearly free electron model again is to treat this term as perturbations to this to the kinetic energy. We treat the potential energy as a perturbation. Okay, so before we actually consider the nearly free electron model, we take an even more drastic approach or approximation, which is called the empty lattice approximation. The empty lattice approximation is essentially the free electron model that we have discussed already, but we take into account somehow that there is some periodicity of the system, in the sense there is a Brillouin lattice and there is a reciprocal lattice. So one way to see that is that the potential is so weak that although the crystal potential is periodic, it's so weak that we can consider it very close to zero and basically disregard it completely. But we can use all the framework that led us to the central equation, meaning that we will assume that there is a reciprocal lattice of G vectors, all right? So basically the empty lattice approximation essentially neglects this term and considers only the kinetic energy term, which is this one, okay? So then this equation becomes very simple to solve. Essentially, there are only two possible solutions of these equations. Either a given coefficient is zero, but they cannot all be zero, otherwise the wave function would be zero. So if at least if one of them is non-zero, then this term should be zero, right? So that gives me straight away the electronic dispersion. E of k is then equal to h bar square k minus g square over 2m. And you see that for each reciprocal lattice G, there is a particular phonon dispersion, electron dispersion, which is parabolic. It's like parabolas, many different parabolas centered in all the different G vectors of your system. So I could in principle add a label G here just to make sure, or to make it explicit, that we have many different solutions, each solution corresponding to a different reciprocal lattice vector. Okay, so we can see an example, for instance, for the case of a 1D crystal. If you remember, for 1D crystal, if I have a 1D crystal with lattice constant A, and then the reciprocal lattice is also one-dimensional and with a lattice spacing 2 pi over A, right? So these are all my G vectors, Z0, G1, G2, minus G1, minus G2, and basically this distance in K space is 2 pi over A. So this is the reciprocal lattice in G space, and what I'm plotting here is the energies. So as I said, using this result, I basically can construct my electronic dispersion by drawing parabolas, many different parabolic functions centered at the different G's. So there's one parabola here centered at 0, this one, and there's, let me use this tool here. So there's this parabola here centered in G equals 0, and there's this another parabola here centered at G1, this one centered at G2, this one in minus G1, this one in minus G2. Okay? So you may be wondering, that looks a bit strange, because when I discussed the free electron case, I had just one parabolic function for the dispersion, right? Just one parabola centered at the origin. And that in fact corresponds to this parabola here, centered at the origin. And now it seems that I have more solutions to my problem, right? Many different parabolas. And indeed, this is a little bit disturbing, and so there is a redundancy in this description, and that's why we can consider not only we don't have to consider the full K space, but only a restricted region of the K space, which is here, which is called the first Brillouin zone. So we reconcile the two approaches by restricting ourselves to K vectors within the first Brillouin zone. And then the two approaches become equivalent. So all the eigenenergies and eigenfunctions that are, let's say, contained or described by this parabola actually correspond to these different pieces of parabolic functions within the Brillouin zone. Each piece of a parabolic function coming from a parabola centered on different G vectors. And you can see that this formalism naturally gives rise to the many bands, to the different bands, electronic bands for electron in a crystal. Okay? So this is basically what we call the empty lattice approximation. And you can see here that in some regions, some special points, in 1D, this is just the boundaries of the Brillouin zone and the gamma point. You see that there are some degeneracies, right? And when you go to higher dimensionalities, for instance in 2D and 3D, as we're going to see, there are going to be even the degeneracies higher than 2. In this case, we have only two-fold degenerate states. This is one-fold, but all the other states are two-fold. And when we go to 3D cubic systems, for instance, you will be able to see that the degeneracies can be much higher. Okay, but then group theory comes and tells us, well, you cannot have arbitrarily degenerate states. Your degeneracies must be consistent with the symmetry group, so the space group of your crystal, so that you can only have degeneracies which are which have the same size of the dimensionalities of your irreducible representation. So group theory will tell us how these different degenerate states break up in specific solutions. And in a way, this is not very different from the many different cases we have considered so far, like crystal field splitting, and in other cases in which you have reduction of degeneracy, reduction of symmetries, leading us to breaking of degeneracies. And we're going to see how this works in practice. Okay. Oh, this is what I was supposed to show, and I think I have already said that. Crystal potential will break some of the degeneracies in high symmetry points and lines, and group theory will tell us how. So, is it this nearly free electron model? Is it good for anything? Well, it describes reasonably well some classes of solids, and especially alkaline metals and metals of the second column of the periodic table. And if you see here, these are, well, if you consider sodium, it's a BCC, crystallizes in a BCC lattice. And if you draw the different parabolas in the empty lattice approximation, this is what you get for BCC. So they look like pieces of parabola, but it's slightly more complicated than we have considered in the previous slide, because now we have a three-dimensional system. So we have parabolas coming from all over in 3D, not only from points in a line, but from different G vectors distributed in 3 dimensions. So we have all these pieces of parabolas here. And this is the empty lattice approximation solutions. And if you compare that with a real calculation of a sodium electronic structure, you see that's not very far from reality. Well, the scale here is not the same, but you can see there's a single parabola here, which is essentially this one. And at this point, it breaks into many different parabolas, which are these ones. And we have different degeneracies. We're going to discuss that. But you see that there's some resemblance between I should not say exact, but very accurate solution of the band structure of sodium and what is predicted by the empty lattice approximation. And the same is for calcium. Calcium is an FCC lattice, and you see again some resemblance between the empty lattice free electron-like bands or parabolas and the solutions, the more accurate solutions. Okay, and you see actually how the degeneracies break at high symmetry points. You see, for instance, here this was a very high degenerate a level with the larger degeneracy, and you see some of these degeneracies are broken, and that's the purpose of using group theory to understand that. Okay, so let's now consider the case of a simple cubic crystal in 3 dimensions. And that's going to be the example we are going to consider for most of this chapter. So a simple cubic system So the Brillouin, sorry, the reciprocal lattices is also simple cubic with a lattice spacing of 2 pi over a, right? So if you consider this to be the G space, and there's an origin here somehow, this is kx, maybe this is, yeah, so this is ky, this is kx, oops, really bad drawing, and this is kz. So you see that these points are located in such a way that this is the gamma point, and this is 2 pi over a. So what I mean is that the set of G vectors are given by a simple cubic lattice with lattice constant 2 pi over a in reciprocal space, and they are linear combinations with integer coefficients n1, n2, n3. So the set of ni are integer numbers, and these are all possible G vectors. I can use another index here, a general index n, just to emphasize that this will give rise to n different bands in my first Brillouin zone. Okay? So now the wave vector k inside the first Brillouin zone I can also write it will be convenient to write as a multiplicative factor 2 pi over a in front of that, and three numbers, psi1, psi2, and psi3. But now these are not integer, but these are real numbers, right? But real numbers, but they are restricted to the first Brillouin zone, meaning that they belong to this interval between -1/2 and 1/2. And so this basically parameterizes or describes all the wave vectors k inside the first Brillouin zone. Okay, so psi are real numbers, and n1, n2, and 3 are integer numbers. So if you use this very convenient notation, and if you go back to this expression here, this expression for the energy dispersions in the empty lattice approximation, basically I can write it, the different energy bands with an index n, so that's one band for each G vector, and as a function of k, this is going to be h bar square over 2m, and k minus g square, right? So k minus g square, there is this factor 2 pi over a square, and here k minus g will become simply psi1 minus n1 square plus psi2 minus n2 square plus psi3 minus n3 square. Okay? So these are a general form for an arbitrary band and an arbitrary k point for the energy of that particular combination in a cubic crystal. Okay? All right. So let's see now different situations, and we're going now to consider, we're going to apply group theory to different points, high symmetry points in the Brillouin zone. And we start with the simplest case, which is the gamma point. So let's look at the wave functions and plane wave solutions at k equals 0. Okay? So if you go back to this expression and consider the gamma point, so the gamma point corresponds to psi 1, psi 2, psi 3 is equal to 0, right? K equals to 0. So for this case, this expression simplifies, and this is what I have in the end. Okay? The different energy levels at the gamma point are going to be given by all possible combinations of n1, n2, and 3 integer numbers, n1, n2, and 3 here. Okay? So let's see a few of them, starting from the lowest energy to and increasing the energy. So the lowest energy solution, of course, is n1 equals to n2 equals to n3 equals to 0. Right? So that gives me 0 energy. This is precisely this level here. Okay? And of course, the degeneracy is 1, because there is only one combination of n1, n2, and 3 that gives me that energy. All of them equal to 0. So G is equal to 0 in this case. So there's only one a reciprocal lattice vector that gives me that energy. And this is symbolized by this 0, 0, 0 refers to the G vector. So this is the lowest energy state. How about the second lowest energy? This one. So where does it come from? Which parabolas contribute to this band crossing? So this is coming from taking one of these numbers equal to 1 and the other ones equal to 0. Either 1 or minus 1, sorry. So there are actually six different combinations. N1 equals to plus or minus 1, N2 equals to plus or minus 1, and N3 equals to plus or minus 1, and all the others 0. Okay? So you can see there are 6 different plane waves that actually are crossing here. So if I draw the degeneracy of this state is 1, and the degeneracy of this state is 6, because there are 6 plane waves. And you can already see that this degeneracy is going to be broken, right? Because in cubic system OH point group, you cannot have a 6-fold degenerate state, because you don't have a irreducible representation, which is 6-fold, which is dimensionality 6. So this is probably going to split, and we are going to see that happening in a minute. Okay. All right. So this is the energy. These are the different wave vectors. So next is this state here. So this, let me draw that again. This is the degeneracy 1, 6. And for this case, we have to, the next higher energy is considering two of these 3 integer numbers equal to 1 or minus 1, and one of them equal to 0. And you can see here that you have 12 different combinations. So this is a very this is a state with a very large degeneracy of 12 here. Okay, and you have all these different parabolas coming from G vectors that are corresponding to these values of n1, n2, and 3. 12 of them. And you can you could keep going, and for instance, the next higher energy state has a degeneracy of 8 corresponding to these plane waves, these G vectors, and the next one would have degeneracy of 6 corresponding to these G vectors. Okay, I think you got the idea, right? So, okay, so let's now see how these different states break up, how their degeneracy break up under the crystal potential. Of course, the lowest energy state is a single degenerate state, so it doesn't, of course, doesn't break any degeneracy. So the next interesting case to consider is this particular one, the second energy level, and let's try to understand that in more detail. Okay. So the idea behind understanding this degeneracy breaking, as I said, is very similar to different situations that we have considered here in this course. So we write down the characters of the equivalence representation, and then we see how this equivalence representation, which is in general reducible, how it decomposes into irreducible representations. Okay. So let's start with the lowest energy level, even though it's not very interesting. But this is G. This is the set of G vectors, which is just 1 in this case, and 1 equals to n2 equals to n3 equals to 0, and corresponds to this point in the Brillouin zone, the gamma point. And what we do is then to apply all the symmetry operations of the point group of the crystal. In this case is a cubic system, so this is the OH group. So these are all the symmetry operations that we have to consider. And we basically want to see, when I apply a given symmetry operation, if that particular wave vector or reciprocal lattice vector is invariant or is mapped into a different one. If that's invariant, then it contributes to 1 in the equivalence representation, and if not, it contributes to 0. So that's the same idea. So of course, the gamma point, it's invariant for any symmetry operation of the cubic group. So this is 1, 1, 1. All characters are equal to 1 for all symmetry operations, right? And this is the totally symmetric identity representation gamma 1. So let's see now the set of 6 G vectors of the type 1, 0, 0. Again, what I mean by 1, 0, 0 is a set of 6 G vectors in units of 2 pi over a, plus or minus 1, 0, 0, 0 plus or minus 1, 0, 0, and 0, 0 plus or minus 1. Okay? So let's see. When I apply the identity, all the 6 of them are invariant. So this is 6 here. What about the C4? A C4 squared, meaning a C2 axis. For instance, this C2 here. This is what I'm calling C4 square. And you can see that when I apply this symmetry operation, only 2 G vectors are invariant, precisely those along this axis. All the other 4 ones, they move, right? So this is 2. Okay. What about this C2 axis? Well, this C2 axis is again a C2 operation, but is now this particular axis, a horizontal axis. And you can see that when you apply this symmetry operation, all vectors move, right? For these 6 vectors, they all move into a different reciprocal lattice vector. So this is 0. And the same for C3. C3 axis is along the main diagonal, so all these G vectors, they swap positions, so this is also 0. And for the C4 is similar to the C4 square, so this is 2. For inversion, they all change. This is 0. If you apply inversion combined with C4 square, then this is interesting, right? When I applied C4 square, I had 2 vectors invariant, and the other 4 G vectors, they moved, but they moved to the opposite, to the negative of themselves. Then when I apply inversion, they go back. So this is the opposite case as this one. So instead of 2 invariant and 4 non-invariant, I have 4 invariant, and 2 non-invariant. So this character is 4. And you could keep doing this. Let me just complete this line. This is a 2, this is a 0, this is a 0. You can verify that. And you see, of course, that if you look at the character table of the OH group, this is a reducible representation. When you decompose, then it becomes this one. Gamma 1 plus gamma 1 2 plus gamma 1 5. You should be careful because, once again, there are 2 different notations. You may, even the book, use both of them in different points in the book. And this could be also this could also be written as gamma 1. This could also be written as gamma 1 plus, and this is gamma 1 plus gamma 1 2 plus, and plus gamma 1 5 minus. And this notation is more transparent in the sense that it tells us right away which are the even and odd representations under inversion. Okay, we have seen that before. All right, so, and these are of course I won't do that for all of them, but these are all the different decompositions that you have for higher energy states. As I said, let me focus initially in this particular one, the second highest energy level at the gamma point in the empty lattice approximation. It was a 6-fold degenerate state, and you can see that right away here that it splits into a 1-fold, 2-fold, and a 3-fold degenerate state. So let's see. So this is an important result from group theory. Let me see if I have a picture. So I can go back to this picture later, but this is just telling me that this particular state, which is 6-fold, it will break into 3 states. I don't know exactly what is the particular order, but let's say this could be gamma 1 plus, this could be gamma 1 2 plus, this could be gamma 1 5 minus, for instance. It's not necessarily in this particular order, but this is what group theory tells me. Okay, the degeneracy is going to be broken in this manner. So let's see how the wave functions should look like. Well, I mean, what I mean by that is that from these 6 different plane waves, I can arrange them in specific manners so that they already belong, or they transform according to these 3 irreducible representations, gamma 1 plus, gamma 1 2 plus, and gamma 1 5 minus. And this is again helpful because it tells me basically it would help me to break up the Hamiltonian matrix. If I expand my wave functions in plane waves, it tells me which particular combination of plane waves allow me to write the Hamiltonian in the block diagonal form, right? As we have seen already previously. Okay? So let me go back to this idea. So the idea is that I'm trying to write my block function as a linear combination. So this is a plane wave times the periodic function that I can write as a linear combination of plane waves in which wave functions are reciprocal lattice vectors, and I can write this in a slightly different form like that. K minus G dot R. Okay? So this is what I call the plane wave expansion of the wave function. Okay? So this is more transparent because it tells me right away that my basis functions are plane waves of this particular form. I don't care too much about normalization here, but they are plane waves of K minus G wave vectors. Okay? These are the basis functions that I use to expand my wave function. So, all right. So now, now let's focus on that particular energy level. Let's focus on the energy level that I could call, let's say, E1, right? Because the ground state is E0 for the gamma point, so the lowest energy state. This one is called E1. And as I have shown, this comes from the set of plane waves 1, 0, 0, right? There's 6 of them. Okay. So for them to describe the wave functions at this particular level, within the idea of a perturbation theory, it's reasonable to expect that from all G vectors, all possible G vectors that contribute to the wave function of those states, the ones associated to this particular set of 6 G vectors are the ones which are going to contribute most, right? This is basically related to the idea that I'm treating the crystal potential as a perturbation. If there was no crystal potential, then that would be just plane waves. All these coefficients would be equal to 1 for these, either 1 or 0, and my wave functions would be just plane waves. But what I mean is, if I go one step further and consider perturbation theory, it's reasonable to expect that for all these basis functions near this energy eigenvalue, the ones that are going to contribute most are those coming from this set of 6 G vectors that I can explicitly write here. So the G vectors that I will consider in my restricted expansion of my plane waves are going to be those that I have already written before. 1, 0, 0, plus or minus 1, 0, 0, to pi over a. 0 plus or minus 1, 0, to pi over a. And 0, 0, plus or minus 1, to pi over a. Okay? So, for k equals 0, and again, we are dealing with a gamma point here, my plane wave basis then is going to be all these different plane waves that I can construct using k equals 0 and all these different g vectors. And these are simply e to the plus or minus I to pi x over a, e to the plus or minus I to pi y over a, and e to the plus or minus I to pi z over a, right? And for short, I'm gonna use the notation 1 plus or minus 1, 0, 0, as I have written before. 0 plus or minus 1, 0, and 0, 0 plus or minus 1 to indicate these different plane wave functions. Okay? All right. Now, how should I write then combinations of these 6 different plane waves that transform according to the different representations that I'm interested in? And then I write again here the character table of the OH group. So this is the OH group. And these are the different representations that I must consider in this case: gamma 1 or gamma 1 plus, gamma 1 2 or gamma 1 2 plus, and gamma 1 5 or gamma 1 5 minus, right? As I have already seen, these are the 3 symmetries that appear in the case of this particular energy level. Okay, the 6-fold degenerate breaks into this set of 3 states: 1 non-degenerate, 1 2-fold degenerate, and 1 3-fold degenerate. And now it's helpful to look at the basis functions. This is 1, or it could also be x squared plus y squared plus z squared. And for gamma 1 2, I look at this set of functions here. And for gamma 1 5 is x, y, z. And this helps us in constructing the different symmetrized linear combinations. So, of course, for gamma 1 plus, we expect a sum over all plane wave states, right? So this is really reasonable to expect, and I'm going to demonstrate that this is indeed the case, that for gamma 1 plus, the properly symmetrized linear combination is going to be simply the sum. You can add some normalization here, but it's going to be the sum of 1 0 0 plus minus 1 0 0 plus 0 1 0 plus 0 minus 1 0 plus 0 0 1 plus 0 0 minus 1. Okay? Now, what about gamma 1 2? Gamma 1 2 or gamma 1 2 plus? For gamma 1 2 plus, if you remember, the basis functions are x squared minus y squared and 2z squared minus x squared minus y squared. As you can see, these are even under inversion, right? So how can I write something similar to that using plane waves? Well, how can I construct even and odd functions using plane waves? So if I make the correspondence x squared to a cosine of 2 pi x over a, because a cosine is even under inversion, right? So this is a good starting point. And other combinations like that, like y square cosine of 2 pi y over a, z square cosine 2 pi z over a. And for odd functions like x, y, z, if I take the sine of 2 pi x over a, then that's probably a good idea too. Okay, so let's try that. So how can I make those linear combinations? So this is easy, right? Because I can just transform exponential functions into cosines and sines. So a cosine of 2 pi x over a is simply 1/2 of 100 plane wave plus minus 100 plane wave, right? And the sine of 2 pi x over a is 1/2i 100 minus 100. So I can just go ahead and use this recipe, right? And because I know already how the basis functions look like in terms of x squared, y squared, z squared, so I can just go ahead and use that, and I can write the first partner of the gamma 1 2 plus representation, the partner that I associate to the basis function x squared minus y squared. I can write this as a 1/2 x squared. What is x squared? X squared is 100 plus minus 100, right? So this should be 100 plus minus 100. And minus y squared, and y squared is 0 10, oops, minus 0 minus 10. So this is a good guess, and you can always try to check that if that transforms according to the different under the different symmetry operations of the group, if transforms like it should be, right? But this is, I mean, we have done that many times already, so we are starting to be very confident in our educated guesses here. So, and the other partner, so the other partner should be similar to 2z squared minus x squared minus y squared. And there's some normalization factor here that I can take care of that later. And this should be then 2001 plus 200 minus 1, which is 2z squared, minus x squared minus y squared. And if you can verify that the normalization here should be 1 over square root of 12. Okay, looking good. So finally, the gamma 1 5 minus. So this is gamma 1 5 minus. This is an odd representation and transforms like x, y, z. So a good guess in terms of plane waves is just to choose the sine instead of the cosine, right? So then I think I can write the three partners for gamma 1 5 minus x. Don't care too much about the I factor. 100 minus 100. This is the x partner. The y partner, it's 0, 1, 0, minus 0, minus 1, 0. And finally, the z partner is 1 over square root of 2, 0, 0, 1, minus 0, 0, minus 1. Okay, these are the linear combinations that transform according to the different irreducible representations of the group. Now, if you look at our textbook, just a brief note. If you look our textbook, it starts from it gives us a different set of linear combination for the gamma 1 2 plus representation, which is this one. So this is we also have seen this before, right? This is it takes the two basis functions as x squared plus gamma y squared plus gamma squared z squared, and x squared plus omega, sorry, not gamma, omega squared y squared plus omega z squared. Okay? And omega is e to the 2 pi I over 3. So, but this is completely equivalent to what we have done. So these are the degenerate states. So any linear combination of those, it will work fine. It will give us the same character. So, and you can see right away that you can transform one into the other using a linear combination, right? So if you write this as let me call that gamma, sorry, psi gamma 1 2 plus, and let me call that psi gamma 1 2 plus minus. So one is rotating along one direction, the other is rotating along the other direction. And you can notice that if I make this linear combination, I multiply gamma 1. If I multiply psi gamma 1 2 plus by omega, and I sum with omega squared multiplied by psi gamma 1 2 minus, and if you do the algebra, this is just omega x squared plus omega squared y squared plus z squared plus omega squared x squared plus omega y squared plus z squared, and this is precisely 2z squared minus x squared minus y squared. So this is precisely this linear combination that I have considered, I have decided to use. And if you do the subtraction, so if you take omega gamma, sorry, if I take omega psi plus minus omega square omega square psi minus and if you do the algebra, you're going to see that this is just x squared minus y squared. You can check that. and this is precisely this other linear combination. So what I'm saying is that you can choose to either work with this linear combination that I have decided to work with, or the ones that you have in our textbook. They are both equivalent and equally good partners of the representations of the gamma 1 2 representation of this particular energy level. Okay? All right. So this is all I wanted to say about the gamma point. Now let's go away from the gamma point. First, let's go to the delta line. The delta line, as you can see here in this picture of the first Brillouin zone, between gamma and x, there's this delta line. And what I'm going to do now is just to show how one can use compatibility relations to see how the different energy levels at high symmetry points are split when you move away from these high symmetry points. Okay? So at the delta line, the group of the wave vectors is C4V. These are the representations, these are the symmetry operations. And what I do is that I start with the gamma 1, gamma 1 2, gamma 1 5 representations at the gamma point. And I'm going to do this very briefly. I just find the characters for these different symmetry operations, and then I decompose into this irreducible representations of the delta group of the wave vector. And what one notices is that gamma 1 goes into delta 1, gamma 1 2 goes into delta 1 plus delta 2, and gamma 1 5 goes into delta 1 plus delta 5. Delta 1 and delta 2 are non-degenerate representations, and delta 5 is a doubly degenerate representation, or doubly a twofold. It will give rise to a twofold degenerate state. Is a 2D representation. Okay, and this is what I meant here when gamma 1 goes into delta 1. Actually, the lowest energy state is also gamma 1 plus or gamma 1. And you can see here in the delta direction goes into a delta 1. And these three states, gamma 1 plus, gamma 1 2 plus, gamma 1 5 minus, when you move away from the gamma point, they break the degeneracy into delta 1s and delta 1, delta 2, delta 5, and another delta 1 here. Okay? We're going to work with some problems regarding this compatibility relations in the problem set. So we are going to get used to do that. And let's move on. Let's talk about the X point now. Let's see how the plane wave solutions at the X point look like. In general, the X point, I'm talking about energies that look like that. At the X point, for instance, the X point in the simple cubic lattice is pi over a 0, 0, right? So meaning that psi 1 is 1/2 and psi 2 and psi 3 are 0. Okay? So this is then, I can write this as 1/2 minus n1 square plus n2 square plus n3 squared. This is the general solution for the energy levels at the X point. And then for the different energy levels, I should vary n1, n2, n3 but keeping them integer, always integer numbers, right? So we can look into the different energy states. Today we're going to discuss the lowest energy state at the x point, and next time, the next lecture, we're going to discuss the higher energy state. But today let's just consider the lowest energy state. And the lowest energy state I obtain by doing n2 equals to n3 equals 0. And I have a double degeneracy here, meaning that I can either take n1 equals to 0 or equals to 1, then I have the same energy, right? So then what happens at the x point is precisely that. So let's see, I have the gamma point here. I have a plane wave coming from 2 pi over a, and the x point is right in the middle, kx equals to pi over a. So I have a parabola coming from this gamma point and another parabola coming from this g vector to pi over a, and they meet precisely at the same energy at the boundary of the Brillouin zone, which is the x point. Okay, so there's a twofold degenerate state here. And let's see how group theory tells us how it splits. So let me so the two wave functions that I'm discussing here, one comes from what I should call G0 or gamma point, which is 0, 0, 0, and that gives me a plane wave that I can call psi 0, which is e to the I pi x over a, right? And the other solution coming from G1 is 2 pi over a 0, 0, 1, 0, 0, and that gives me another plane wave that I can call psi 1 e to the minus I pi x over a. Okay. All right, so let's go ahead. What is the group of the wave vector? The group of the wave vector at the x point is d4h. This is the character table for d4, but d4h is the direct product between d4 and the inversion group. So just to save some space, I didn't write down the complete character table here. I'm just writing 1/4 of it. But you see, you know that I have, if I combine this with the inversion group, then I have even and odd representations, starting from these representations of the D4 group. Okay. Now, so what I have to do now is to write down the equivalence representation for these two plane waves. Let's write it here. The characters for the equivalent representations, and remember that I'm considering this two plane waves. Let me write here e to the plus or minus I pi x over a. So I have to consider these two states and see how they transform, if they remain invariant or if they change into the symmetry operations of the group of the wave vector. Of course, for the identity, both of them remain invariant. For the C2 operation, C2 operations is a rotation by pi around the x-axis. So character is also 2 here, and the same for C4, because this is also a rotation around the x-axis. But if I do rotations around the C2 perpendicular axis, you see that this is going to be 0. This is going to be 0. The inversion also is going to be 0. This is all 0. Except for this guy. This guy swapped the two plane waves, but when I apply inversion, they go back to what they were before. So this is a 2 here, and this is a 2 here. Okay, this is the equivalence representation. And you can decompose it. When you decompose it, you will see that this is the sum of x1 plus and x4 minus. It's the sum of even and an odd representation of this group. Okay, so there are two different notations, Schonflies and the other notation for the group of the wave vector, and for each one of those representation I can either have plus or minus, depending if they are even or odd. Okay. All right. So this is how they should look like. And actually, if I go back here, this is telling me, this is precisely what I have written here, and this is telling me when I approach the x point here, this is the lowest energy state I was considering, the degeneracy is broken. So there is a gap here, and one state is x1 plus, the other state is x4 minus. This is, by the way, this the magnitude of this gap you learn in basic solid state courses, that this is proportional to, I think it's twice the magnitude of the Fourier transform of a crystal potential associated to this G vector. So the magnitude of this gap is going to be the absolute value, 2 times the absolute value of the particular G component of the crystal potential, 2 pi over a 0, 0. Right. In any case, so let's go back here and let's try now to write down the wave functions, properly symmetrized wave functions for x1 plus and for x4 minus. And once again, this is not very hard to guess. There are only 2 possible linear combinations, plus or minus, like bonding and anti-bonding combinations. So it look like bonding and anti-bonding. So one is a symmetric combination of 0, 0, 0 and minus, 1, 0, 0, and this gives me twice 2 times cosine of pi x over a, and for x4 minus symmetry I have I subtract one from the other, and that gives me a sine, 2 times sine of pi x over a. These are even and odd under inversion. Okay? So this is the group theory for the lowest energy level at the x point of a cubic crystal. And starting from next lecture, we're going to see higher energy levels at the X point, and then we are going to see what is the effect of glide planes and screw axes on these band structures. Okay, thank you and see you next time.